Very good morning, all. So, I hope now you are enjoying the programming with greedy algorithms. Fractional knapsack was one of the interesting starting problem. And subsequently, yesterday we talked about activity selection problem. Uh, you can easily see that programming with greedy algorithms is not difficult. Understanding the concept is also not difficult. The only important aspect is ensuring that the optimality or the greedy choice to be the best or the safest or the best optimal. So before we proceed further, let me just have quickly a discussion of the coding corresponding to the activity selection so that those who have not implemented completely, they get a feel of that. So I have defined here activity as a structure. This you can otherwise take as a 2D array also. So activity array can be taken where index 0 can be taken to use the start and index 1 be taken for finish. So either you take it as a 2D array or array of structures, one and the same thing. For storing which activities got selected, I have taken an answer set, initially global. Of course, you can avoid global also, which will be even a better proportion. And then I have corresponding functions. So of course, the sorting will be needed. So just quickly have a clarity of the how main will be there. So I have an array declared of certain activities, array of structures. Of course, I told 2D array is another option. And then number of activities read. Now activities wise starting time and finish time read. I'm reading it from 1 to n so that 0th is free for dummy indexes or so the dummy activity to be added, etc. So I added a dummy activity which finishes at -1 time and the dummy activity n plus 1 as we discussed for this will be needed mainly for recursive calls. For iterative, it will not be needed, but still I have implemented dummy activities also. Sorting to be done, sorting based on the descending order. So any sorting algorithm, but sorting based on the ascending order of the finish time done. And then, of course, if I want to just check, then done. Recursive call, corresponding result. Non-recursive call or iterative call, corresponding result. And printing the activities selected through answer set. So going one by one, activity selection using the iterative call. So array of the structure passed and I and j. Of course, if I'm making iterative call, parameter will be simply 1 and n, 0 and n plus 1 not needed because dummy activity is non needed. They can be directly called. So as we said that we will start by taking selected activity to be the first activity. So I'm starting with the 1 will be guaranteedly selected. And then from 2 onwards, I have to find out which of the activities are going to be compatible with the last selected and accordingly add them into the answer set. So initially job number 1 or activity number 1 or in a general I is counted in the answer set. Now I'm checking from 2 onwards up to n and that I'm checking if that activity start time is greater than or equal to the finish of the selected one means this is compatible. This can be added into my selection. And now my last selected will be this particular activity. If it is not having the start time, that means it is not compatible with the last selected. This is to be ignored. In ignored case means k will be incremented. And in this case also, if selected, k will be incremented. So every time the next activity will be checked for the corresponding availability or compatibility with the last selected. And accordingly, some of them will get selected and I will have the final answer ready. So that way I can easily do. On the other hand, when I talk of a recursive implementation, I will be calling it with dummy activities 0 and n plus 1. And I want all activities which are compatible with A0 and n plus 1 to be found. So I will say, fine, current selected activity is I, that is A0 initially and subsequently whichever gets selected. The activity to be checked is called as a next activity. So from I plus 1 onwards, it will be checked. And I will be checking if the next activity's start time is not compatible with the finish time of the last selected, that activity is to be ignored. Recursion means effectively whenever a new greedy choice becomes a final, that will be included and recursively again called. So I will keep on incrementing next till I don't get the corresponding activity. Of course, next could reach to the final stage also. That's why I have this additional check. So if I found an activity, means next will be guaranteedly less than j. That means a new activity has been found which is compatible with the last selected. So I will be adding that into my answer set. And now the call will be that selected activity, the last selected is this next. So this will replace I, and j is the final boundary. So 1 plus this current activity is, because of that it is 1 plus, and then recursive call coming for the selected being next onwards to be recursively found. Whenever I reach, or if I am not able to find and reach to the boundary, I will say this recursive call will return 0. So simple, and I can easily do, and then accordingly sort and print, etc. can be written. So probably this much code is sufficient to revise your implementation, and I'm hoping that now you can easily do that. So having said that, now let's resume back to our discussions for the today's topic. So I'll say, fine, today what we are going to see. So we are going to discuss some more interesting algorithms today, and what are going to be those algorithms have effectively come from some domain of electronics also. So to be precise, those things, what we are going to talk is one of the coding scheme which probably started with electronics domain. So coding scheme, one of the researcher from MIT, his name was Professor Huffman. So he has suggested one Huffman code, and Huffman coding is the topic which was effectively used a lot with electronics engineering for coding various signals and having the size reduced according to the requirement. So before Huffman coding, if I remember, this is as old as 1952. So at that time, concept of a greedy algorithms, etc., was not discussed because computers were just in the infant stage. But this code was developed at that time. And when greedy algorithms were identified, it was found that Huffman code is also actually one of the best greedy algorithms to be discussed and proved also. So this was the optimal solution with a greedy choice. So we will talk of this very interesting problem today. So the problem was effectively that it said that a variable length code for various alphabets or any strings to be done can be a better choice than a fixed length code. Of course, why did we do coding? There could be many reasons. So let's understand all that with help of an example. Let's say there is a survey being done for best movies, best Hindi movies, let's say, of last 5 years. So there is some public survey being done, and of last or for period, let's say 1917 to 1922. So this period. So let's say there are 10,000 people, and each person to tell 10 best movies. So the name of 10 best movies to be given. Now, effectively, that means there are going to be total 1 lakh movie names which will be told. And I want all these names to be stored, and then these are to be transmitted over a channel. So there will be a channel, and of course, initially the channel capacity was less. So transmitted over some communication channel required a lot of time to send such a big data. And hence they wanted this data to be reduced with the size. And if I say each movie name could be, let's say, of maximum 50 bytes, that will mean that I'm going to effectively transmit 50 lakh bytes. So the data size is quite big, and over slow channels, it will take a lot of time. So reduce the size could have been one option, and reduce the size of the file can help in faster transmission. For that, the solution was that why should I have such a big file to be sent? In situations like this, if you say total 1 lakh movie names, but probably you can say best movies which almost all people will vote for could be maybe out of some good movies, say 25, 30 normally. I know that most of the people will prefer these movies. And so best movies or very good movies which were in the last 5 years could be 25, 30. So some person P1 will choose 10 out of these maybe. P2 will have some other 10 out of these. So mostly I will say my 1 lakh file will have effectively 25-30 movies name. Let's assume maximum 30 names, but with repetition. For example, when I today talked in the class and asked which are the best Hindi movies you like, so some people said KGF 1, some people said KGF 2, some people said, say, Kashmir Files, maybe few more names like that. But that effectively means maybe some 20K people could name, say, KGF 1. Maybe another 18K could mean KGF 2. Some maybe 19K could mean Kashmir Files, and like that. And there will be few names which will have maybe 500, which may have, let's say, only 1200, and something lesser than that. So effectively, what I mean is that if I have 50 lakhs data sent versus I say these 30 movie names to be given some code, and that code is sent, that will be better choice. For example, I say there are movie 1, movie 2, and let's say movie 30. I will give them some binary code. So 30 movies means I can have a 2 raised to 5, 32 bits, 32. So I can have 5-bit code for each movie. So maybe I will say this code is given as 0000. Some movie name is given 0001, and then similarly 00010, and so and so. So I could have 11100, something like that, or maybe 11101, whatever. So we can have these 30 codes and 5 bits are sufficient. But that will effectively mean 1 lakh movie names with each name now being sent with a 5 bits will mean only 5 lakh bits to be sent. Earlier, I was sending 50 lakh into 8 bits, 50 lakh bytes. So 5 lakh bits versus 50 lakh into 8 bits. Effectively, I am able to have 1/80 size of the file. So that's the advantage of coding of the file. Now, if I can achieve that, probably that can be the best. But of course, I have to think of doing the decoding also. So for decoding, I will need to know that, okay, 000 means M1. Say 00100 means, let's say, M5, and so and so. So that will mean this table, which I have just tried to store, this will also need to be stored. So a table will mean movie 1, that means, let's say, 50-byte name, and correspondingly 5-bit code. So this table means effectively 30 entries. So this is an extra information to be said. 30 into 50 into 8 is these many bits, into 5 bits for each. So these many bits extra needed for decoding, so that over the other side, I knowing this code, I can easily use this for the decoding purposes. But effectively, that means that my total size reduces significantly. Still, it is approximately 1/80. This is a very small size, so not a big issue. So I say, hence, coding is very useful. But before Huffman coding, this fixed length coding was being used, and people felt that this code is good enough. Huffman said, no, don't go or be dependent on that. So Huffman code said, we will have a variable length code. Obviously, I say that he had a thumb rule, or he had some greedy choice made, and that greedy choice ensured that the optimality still remained. Can you think of what can be the greedy choice? Variable length means, of course, some movies will have a smaller code of maybe length 1 or 2 or so, and some may have more than 5 also. Earlier we had fixed, but now I say this will be there. And he proved that this will be a better choice in such situations. But what should be the greedy choice? How should we decide that which movie should have a smaller code? Obviously, you have some intuition in your mind. You have a greedy choice in your mind. And the choice can be, obviously, I will say that the movie with more frequency should be having smaller code. Obviously, for example, I say if my KGF movie has 20K entries, so if I have this code to be of 1 bit, instead of sending 20K into 5 bits versus 20K into 1 bit, I will be saving a lot. On the other hand, if a movie had some 500 entries, earlier I was sending 5 bits for that. Now I will say send 500 into 7 bits now. So extra 1000 bits will be sent here, but for KGF, I was able to save 20K into 4 bits saved. So that is the logic, that here for frequency lesser, I will be having a lengthier code, which will take more bits and some overhead. But the movies having bigger frequency, they will save a lot, and overall saving will be much more than the corresponding extra data sent. Hence, it was proved that optimality is guaranteed. And obviously, that guarantee was mathematically proven, and thence we can easily see that we should use Huffman code. So for our example also, we will discuss that and find out that, and that will be useful for us to understand. For example, I say, take a data, and over the data, we will discuss this particular. So effectively, let's assume I have some movie A, B, C, D, E, F. Of course, ABCD is just a abbreviation for the movie, but I'm saying that is a 50 byte name for the movie. And let's say their frequency over the file being sent is something like 45K. This has 13K. Let's say this has 12K. This has correspondingly 16K. This has correspondingly 9K. This has correspondingly 5K. So these many frequencies. So I say 45K frequency happened, 45,000 happened for A, and a total being, of course, let's say 1 lakh. So this is the frequency. So now I say what Huffman coding said was that what we are going to do will be slightly different way of programming and using this, that I am going to think of giving lesser frequency movies a lengthier code, and vice versa also. More frequent big code, or I'll say smaller code. How to do that? So what Huffman suggested, or what we can intuitively also find, that overall, ultimately I have to decide code to be, let's say, 0 or 1. So if there are only 2 movies, one can be given 0, one can be given 1. But I have more than 2, so I will say then the variable length code should be in a way that I should be able to decode also. And in decoding, that flexibility has to be there in some special manner. So what was the requirement? If earlier I had 5-bit code and I have sent, let's say, 00101, 10100, 00100, and so, and so, I could easily say each 5-bit is equivalent to one movie. Let's say this is M6, say this is M28, say this is M5, and so on. So decoding was straight because of 5-bit length. Now, if I have variable length, now that is going to be a problem. Variable length means somebody has a code 0, somebody has a code 1. If somebody has a code 0, 1, say if I have one code 0, one code 1, 1, 0, 1. Now, if I am sending this code onwards, how to decode? How to decode? Because the problem is, if I have no separator in between, this could mean one movie, let's say M1, this is M2, let's say this is M3. Then this could mean M2, and this could also mean again M1, this could also mean M2. Other possibility, 0101 could mean this is M3, this could mean M3. Other possibility, this could be M1, this M2, but this M3, and so on. So there are going to be multiple options. Then probably that meant that either I should give a blank in between to say that if I want to send 0, 1, and then 0, 1, so I'll say I'll send 0, 1, 0, 1. This meant M1, this meant M2, and obviously this meant M3. But extra blank means extra byte, and extra byte obviously means more file size. Of course, not a good solution. So what Huffman said, that the code will be a prefix code category. Prefix code category meant that no code will be a prefix of other. That was a fantastic property which helped in decoding as well as faster transmission with a smaller size. No code will be a prefix of the other. That probably appears difficult to do, but my coding will be, for example, something like a 0, 1, 1, 0 could be for one movie, but that will mean this will never be a prefix of other one. That means other code will be something like as 001 or 110, but no code will have 01 and something. No code will have 10 and something. So this will not happen, and other codes should be like this. So having said that, it appears to be easy, but how to implement and how to design? So Huffman designed it in a beautiful manner. Huffman code ensured this prefixing and that decoding was possible. So ensured prefix code. So now we understand what he did. So I say, if I had A movie with the frequency 45, B movie with frequency 13, C movie with frequency 12, D movie with the 16, E movie, let's say with 9, F movie with 5. So what he said, that the movies with the smallest frequency will be given the lengthiest code, obviously, and that will be the starting point. Why? I say, later I will consider them as a merged movie with frequency 14, and now I will apply the same logic overall. Now that will further mean that two smaller movies will get merged together. Subsequently, I will be left with only two movies or two groups. They could be two movies or groups only. And then I will say, I will have one group side, or I'll say group 1 oblique movie as a code 0 given. Other side, which is group 2 or movie, will be given correspondingly code 1. So I am able to differentiate between these two codes, and assuming that there were only two movies, but as I said, they were merged and considered, so later they also need to be differentiated. So he said if they were earlier merged, that effectively meant they further had some grouping, they can be further given 0 and 1 and like that. So intuitively, I can understand that this is going to be a beautiful algorithm and should work. Of course, we will prove it's safe for optimality, but let's understand how does it work. So the philosophy and the intuition was clear that the movies with the smaller frequency should be given lengthier code, and movies which have more frequency, for example, 45, so that should have the smallest code. And how to systematically build, I will have grouping done, and that helps. How that will help? Let's see. I will say, first of all, let's keep them in order of their frequency. That will make my work easier. So I treat each movie in the ascending order of a frequency. That is going to be my logic. So whether I need sorting or not, I will see later. But initially, for understanding, I arrange them and just see that how I will work. So that it doesn't go out of page, I am writing A45. So at present, it is a node with a circle, and I'm using that. On the other hand, when I will be using, just let me take another pen. So initially, I have this F5 and this 9. I'll say these two are the smallest ones. So they should be towards the lengthiest codes. That means they should be treated as a single group, and overall single group will have some code followed by zeros and ones. That means it said, assume this as one node where I have F with 5 frequency, E with 9 frequency, and I will say treat them as one bigger node. So I'm using a different pen and a different color and a circle to show internal node where I have a frequency. So this I will say it's an internal node, and this I had is a leaf node. So this node I am showing as a leaf, which is rectangle based, and the internal node is effectively circle or L, this circular based. So I'll say remove these from the list, and now I have a node with 14 frequency. But 14 frequency indirectly has disconnections. From here also, I will take 2 nodes with the minimum frequency. So I have correspondingly C and B. C is 12. So I will say, let these also be get connected. So I will say, accordingly, I have these 2 to becoming another node of a 25 frequency. And the correspondingly, I have got C here with the 12 frequency and B here having 13 frequency. Now, these 2 gone, and I have 14 node, 25, 16, 14. Again, a 2 to be taken. So this is a 14, this is a 16. So these 2 will be taken out. And once these 2 are taken out, I will say, for uniformity, I keep the left side with a lesser value. So I will mean there I will get another node with 14 plus 16 frequency, where this is the left side, and I will have this merged node with D as 60. So now I have a node with size 30. So 14 removed, 16 removed, and I have another node with 30. So now I am left with 30, I am left with 25, and I am left with 45. The process to continue. Later I find that 25 and 30 are the smallest. So 30 is one node, this is another node, they will be combined. So I'll say I will have another node which will become of a frequency 30 plus 25, and 25 has a left node as 55 has left node, which is equivalent to this 25. 25 indirectly meant that it had actually internally C12 and B13. Now this also removed, this also removed. So I'm actually left with A45. I'll put it with other pen. So I'm left with A45 is one node left, and other node left is with this 55. So that will mean now these to be combined. That will mean overall I will have a node with 100, where the left side is correspondingly A, which is 45, and right side I have the node with 55 frequency, but it is an internal node. It means it further has two children, one of 25, other of 30. It means 25 further has two children, 30 has further two children, and correspondingly, if you see, this is C as 12. I can just see from above this and this, B as 13. This is correspondingly 30 has further another leaf node, another internal node of 14, and corresponding to 13, I have F as 5, I have E as 9, and I have B as 16. Now, this becomes overall a Huffman tree. And I say that I wanted, actually internally Huffman said that a treat that you wanted to code A versus this new node. These are to be coded. One is having frequency 45, other is a 55. So obviously one side I will give code 0 and other side 1. So anything which is a part of a 55 has this code 1 onwards. Of course, then he said, now 55 has no further children. So this code, he said, let's increase the length of the code. So as long as there are two movies, if two movies only, then the code can be, I can easily say, if two movies, code will be one length. But if you have more than one length, then that will mean I'll just shift my page slightly. So one length only. But if the code has more depth, there are more movies which contributed towards 55 said, again 0 and 1, again 0 and 1, again 0 and 1, again 0. Having said that, I will just carry forward this page with me on the other side, and I will write here now. So I say, now based on this, if you see carefully, my movie correspondingly A, the code is ready. A code will be start from the root 0 code. B code is, where is B? Here. So start from the root, follow the path, and you have 1, then 0, and then 1. So my B will have this code. What will be the code for C? C is here. So that will mean I will follow the path of this root. That will mean the code is going to be 1, then 0, and then 0. Similarly, for the D, the code is going to be 1, 1, 1. Similarly, for the E, E is here. So E code will be 1, 1, 0, and 1. F will be 1, 1, 0, 0. So effectively all codes ready. Now, the advantage of all this code being no code is a prefix of other. We will show and prove this. For example, if I was sending some data 10101100101100, something like this, if this was being sent, I say start from here, your code will be guaranteedly decoded without any separator, without any blank needed. 1, only 1, nowhere, no issues. 0, 1, 0, nobody's code. 101 is a code of B, and before that 10 was nobody's code anywhere. Nobody had only 10 as a code. So this will be treated as B. Then I have 0101. So I say 0. Only 0 directly matches with A, nothing else to be done. Don't go beyond 0 because 0 is nowhere used else. Again, 1, 0, 1 means again B. Then 1, 0, 0, C. And only 1 or 1, 0 nowhere comes. Again B. Again A. Again A. Maybe I have 1, 1, 0, 1. Again A. Again, this will mean 1101 will mean E, and so on. So all that becomes straightforward decoding guaranteed. Hence, this coding has an excellent opportunity. So what Huffman said that this process can generate your variable length code, and now you easily see if my A was 45K frequency of A, it will be transmitted with 1 bit size, but character F, which was, or character E, which was only 5K, that will be transmitted with a 4-bit size. And I had total 6 movies. That will mean effectively 2 raised to 3. That means the 3 bits could have been sufficient if I had fixed length code. So in case of a fixed length for A also, I could have transmitted 3 bits for each K A 45K times, but now I will transmit 1 bit for each of these. That is the whole purpose. But I have said, is greedy choice optimal? I have decided like this, is greedy choice optimal, or what was the basis of this? And how did I decide, or the property I identified? Of course, intuition was there, but intuition could have started with a higher frequency movie also to be given code. Yes, you could start from there, that A to be given 0, but then next, if you give a B, or let's say some other movie, next highest movie was with 16D. If you say D given 1, then what about others? Others will have a prefix of either 0 and 1. So other movies code will be not possible because prefix will happen. 0 or 1 will be used there. And if one of them is a prefix, decoding will become a problem. So starting with the highest frequency was not a solution. Starting with the lowest frequency could have been a solution. But is this the best choice? Is this going to be working always? Or what is the mathematical proof to say that this greedy choice is going to work? And what is how I decided the basis of this? So we will see what was the property which he decided, and we understand that. And then we will see the optimality proof also, and we will understand that also. So both of these are mathematically proved in the book also, in the lemma 16.2 and 16.3. And they actually tell why I should accept this as a greedy choice. So just I will stop this, my sharing of this, and I'll go to PPT mode, and I'll just show you one PPT where I have this information to be shared with you. So I say now, corresponding to this, what is the property of the greedy choice? I will say the book has given this as that it says, let C be an array in which each movie has a frequency. And let me just have a pen, in which each movie has some frequency, C dot frequency. And we said, I'm going to choose X and Y of 2 lowest frequencies. And once you have the lowest frequency, I will say they will be given a prefix code optimal such that they differ in only last bit and their length is the same. Having said that, I'll say this is already explained in your book also. And just I will say that theorem 16.2 proof you should read, but I will just explain what does it mean. So it says effectively we chose E and F as the two movies with the same frequency or minimum frequency, and based on that frequency, they were considered to be the children of the same node. Same node children means they are going to have the same length code, and one of them will be given last bit as 0, other will be given last bit as 1. So I'll just say, fine, let me go back and show you what we just discussed and see. Now I go back here and see here, if you see what we have done, E and F to be the same length code will come. Same length code because they are children of the same node. How they will get the same length? Up to 14, everybody will get an initial code which is going to be prefix for F and E both, and F will get a 0, E will get 1 added for the code differentiation. So F and E differ here with the 1 bit, and rest code they have seen. Then I say, assume that there was some movie with code 14. Had there been a single movie, the same logic was still applicable, and I could have done like this. So similarly, I said B and C, they have the same length code, assuming that at that time they were the smallest, because other movie is the corresponding 14 length. So 14 length, any movie which is a part of 14 length, they have unique common code as 110. 110 will be later added extra. And then I said, similarly, for 25, I have this. So that logic looks to be okay, but is it optimal? It appears to be a good greedy choice that intuitively should give me the solution as a local or current best. I can easily see current best, I can easily smell to be the best choice by starting with that. Good enough. But is it best? Is it safe? Is it guaranteed? Is it optimal? I have to prove that. So for proving optimality, I will say that intuitively okay, but optimality, I have to prove that what optimality means, that if nodes X and Y which had lowest frequency, if they are merged together, and now that Z node is used for further steps with new frequency, is it going to be optimal or not? Probably yes, but I have to prove that also, because this is the step I have followed. That initially choice was optimal. The process which I followed, that let's replace that and treat it as one common node, and still it will lead to the answer which is going to be optimal, that I have to prove. So again, stopping this sharing of this, and let me show you another property of the same. Let me just correct this also. This is TWO. So I, sorry, just correct that. Good enough. And then I'll save this. And then now I again go for the next proof. So this I have already discussed. Then I say optimality proof. So again, there is a theorem given in your book, a lemma given, to be precise, lemma 16.3, which says that initially you had X and Y. Later, you make a new array C dash where X and Y are removed and Z is added with a new frequency. So it is proved that the T dash, which will be made for the new Huffman tree using Z, will be still an optimal tree, and that is what we are targeting to achieve. So in the book, it is mentioned that it will be still an optimal tree later, where the Z will be actually replaced with the corresponding X and Y as children, and they will be given one extra bit for the length. How it is proved? It is proved by using total cost of the tree being calculated. The total cost of the tree is defined by corresponding frequency and the height or the depth or the length of the code, and using the same concept, that will be still applicable. So I say that if I just want to see that this is going to be the corresponding optimality proof, and it says replacing Z and later Z being again replaced by X and Y as its internal children, then it will still remain optimal. Of course, intuitively we can understand. Mathematically, this is proven by using the corresponding concept. So proof effectively uses cost of the tree, and cost effectively is equivalent to saying frequency into the corresponding length of the code which will be assigned. Length actually indirectly means depth of the nodes. Based on the depth, the length will be actually calculated. So it says use this cost for the T, as well as then from there the new tree T dash, and then you could easily see optimality guaranteed. So if that optimality is guaranteed, then I can easily use the same concept to have this one. Of course, read that. If there are any doubts, we will discuss next time. But for me, the more important aspect now becomes is the implementational issues. So implementation and logic, but of course, conceptual clarity of the mathematical proofs or lemmas is also needed. So that also you should study. And in interviews, the conceptual discussions are normally done. Conceptual clarity will be expected from you during your interviews, etc. So if you read that, it will be useful. And implementation. Effectively, I will say that I needed every time 2 nodes or movies, initially movies, later they will become some collective nodes with minimum frequency. So min needed. Sorting can be one option, but of course sorting means next time one new node will be inserted. So 2 will be removed, 2 nodes or 2 will be removed, and 1 will be added every time. Sorting won't be the best solution because insertion will take more time in sorted array. Hence, obviously, priority queue oblique what you say as a min heap can be the good choice, as we did in graphs also in MST or in Dicastra. So as I need extract min kind of a thing, so I can use that. So I say if my C is my array of movies, so then I can treat them initially as a PQ. So I will say PQ equal to this C array, or say I'll say ARR in general. Let's say ARR is an array. So PQ is array. This is actually equivalent to say build heap, because P is initially having the frequency along with the movie name, and build heap will mean root gets the movie with minimum frequency. And that is what we will need. So my PQ is made, and that is effectively internally calling the build heap. Once PQ ready, every time what I have to do, extract one node. So I'll say, let that be called as a Z. So I will be doing extract min from PQ. That already I have done. Similarly, I need second node Y. That will be extract min, obviously. Now what to do? I have to create a new node where X and Y will become its left and right child. So that means I will need a node. So I will say, okay, create a new node. Let's say called Z, and Z dot left. Syntax can be anything. Whether I will use a dot or arrow, I can see later. But effectively that I will use this. Similarly, could be Z arrow right equal to Y. So Z is created and Z's frequency to be defined. Z's frequency will be equal to X frequency plus Y frequency. Dot or arrow, you can easily decide later, but this is effectively Z ready. Now what next? we are supposed to insert this node. Let me just put it somewhere down further. I can't do that. Fine, good enough. So if I have to now insert Z into PQ, of course, I will keep on doing this and I have to repeat this every time. How many times? I have to think of. Every time two nodes are removed and one inserted. Two removed, one inserted means total nodes keep on reducing by one every time. So if initially there are n nodes, n minus 1 times loop will be sufficient to reach to the root, and once I come out, only one node will be there into the PQ, and that is going to be the answer, or that is going to be the corresponding root of Huffman tree. So this root we will need to have the tree generated. Why I am discussing in all this way? I am making sure that I am maintaining the modularity of the programming. I'm saying I'm implementing it in two ways. First, generate your Huffman tree. I call that as generate as a Huffman tree, HT. Once a tree is ready, I will be generating the code over Huffman tree. Generate code for each leaf node, and leaf effectively means this is going to be an external node, non-internal node, because external node will have the movie name, and internal mode or external means effectively rectangle shape, which we have shown in our code. So effectively, this is leaf node means external shape, and for each leaf node, code will be generated by using 0 and 1 recursively at every length or at every depth. At every depth, I will keep on adding 0 and 1, and that will be the corresponding logic. So these are going to be two modules, and this will be done over your generated HT. The HT which you generated in the first step. So HT should be returned. Of course, both can be combinedly also made, but for better modularity, you should follow this. So what about module 1? More or less, the code is already written, logic written. But of course, that will mean we have to think of the node structure, that heap or PQ of nodes of what? I need sometimes, so I need a structure. Of course, the corresponding node, what will be its properties? Of course, movie name. So I can say char name, let's say 50, or effectively it's a data, any data which you wanted to encode. You need frequency, obviously. What else you need? Probably you need a left pointer, and you also need a right pointer, because for certain nodes initially, even if it was not there, now I need. And if you see carefully, I'll show you the previous Huffman tree. In this, it's not going to be remaining the binary, complete binary tree. If you see, it's not going to be a CBT, because some node will have left child, some node will not have. If you see carefully there, A's children didn't exist at all. If A's children don't exist, obviously the array-based storage is not sufficient. Array-based implementation of PQ not working, not going to work. And because I cannot guarantee the indexes to be in the order of left child being on 2i and right child being on 2i plus 1, not guaranteed. So I will need effectively pointers. So I will say what I actually need is I will need a struct node pointers. Yes. And anything else? Probably not. So more or less, I need all these properties. So by using this, then I can have my PQ to be array of pointers to nodes, because now I will use left and right pointers to be appended with the corresponding extra nodes, and somebody will have extra, somebody will not have. So I'll need all this array of pointers. Now, once I say this, this is a sufficient for the implementation which you can attempt, but there is another interesting discussion. So effectively, implementation aspect is more or less over. So you need in my nodes the corresponding frequency guaranteedly, movie name, or the corresponding, I will say, name, and then you need star left and star right. Of course, you can easily do that. But the question is, do we need all these data same time? Do we need all fields same time for every node? So the answer is no. Now, this is needed for leaves only, and these are needed for internal nodes only. But automatically it means that node will use either this or this, not both. One of these two. One only, not both at any stage. No node requires both at the same time. If not, can we have which storage can be useful? You have studied some storage related to this, but probably you have never thought that how to use that. And in this, I say that is going to be an excellent learning of that extra storage, which you have studied theoretically and never used that. Can you recall something? Maybe you are not, or some of you recall, you have studied union versus structures. Yes, now you appreciate what I am talking. In union, the space will be shared, so more optimal. And I can have name as one group. Other group will have the left pointer and right pointer. And union of the two to be taken will mean the memory allocation will be not for all at the same time. Memory will be for the max out of these two groups. But all memory will not be used. In structure, total memory will be summation of all memories. Structure will mean name memory plus left memory plus right variable memory. So in a structure, this all will be plus, but union, it will mean one of these. That is the difference. And in this case, I am clear that I don't need all fields at the same time. I need either this or this, but not both. Hence, union is best. But whenever you use union, you should know that which of node is is being used for which purpose. How will you know whether the memory being used is for the name variable or for the left right variable? Because if you don't know and you try to access, no error will come, but you will probably mistakenly use the same memory. So for that, you will always use a flag. Maybe you will say 0 means it's a leaf node. And if you use 1, you will say it's an internal node. So if left and right, if flag is so, your structure now will be slightly modified, and you should ideally have frequency stored for everyone, flag stored for everyone, and then you will have a union among two things. How to implement, I will leave it to you. Either you will have a name or you will have left right as a one group. pointers. So union of these two things. And flag will be used to differentiate among the corresponding union members. So for leaf nodes, you will be initializing it with flag as a 0. As soon as you create a Z, that will effectively mean flag will be considered as 1. And initial array, all movies were the movie names. So in that case, flag will be correspondingly 0 for each array I. But later, in the corresponding min heap or priority queue, you will have now array of pointers. So effectively, it will mean struct node star PQ, let's say 50 or 100 or whatever you want to give. So it's an array of pointers. And within this, accordingly, you know all, you require min heapify, you require extract min, etc., etc. All those functions you have already done. I need not explain more than that. Coming to the last part, code generation. So module 2, generate code. How to do that? So I'll just give you a quick idea that again it will be recursive because the depth is unknown, number of nodes who will have children or not known. So I will say initially you will start here and you will say, let's say I'm starting with this point. So maybe my starting depth is 0. I'll say k is showing my depth or k is 0. K equal to 0 means code is initially starting with first 0. So I'll say this side code will be 0 followed by recursive call, recursive coding. This side code will be 1 followed by recursive coding, followed by means what? I will say I will have some variable which will keep on storing the code. So in code K, I will store 0 and then I will have left side recursive call. Of course, now with K as 1, effectively means K plus 1 will be used every time increment, later K2 and so and so. And that will mean, say, if I have some initially, let's say 100, I went, let's say this side, say this is some frequency 45, this is a some frequency 55. So I will say when you are going this side, my code till now is code 0 to be equal to 0, this 0, and now a recursive call. If it has some children, that will be given. Otherwise, if it is a leaf, code is ready, and I will say leaf means code ready. So whatever code is ready, the length is also ready, and the 0 to be printed. Code ready, print. On the other hand, you went to this side. So I will say when you come this side, you will say after that you make code for the same variable to be 1 and then now go right side recursive call. With K plus 1, earlier K was 1 and now K plus 1. So I reach here with K as 1 and if further needed, this K1 will be used. 55 has further 2. So that will mean now K is 1. So that is correspondingly this side again the same recursive call will be generated. So I will have code 1 equal to 0 and then a recursive call. So initially this 1 is already stored. Now this is 0 so stored and a recursion going downwards. Here effectively the call will come with K as 2. So next time code 2 will also get either accordingly added 0 or 1 till we reach to a leaf. Whenever we reach to leaf, my k could be, let's say, 4 or 5 or something. Recursion will resume back, k will further get reduced, will go other side with the code becoming again 1, 0 to 1. So first time 0, then this. So code 1 will be 0, and given this, recursively it will go downwards. Then it will say code 1 to become 1, and then recursively over the right side. So all right side code is effectively meaning that your code is initially this one, followed by this one, and then the recursive one will generate further codes. I think this much logic is sufficient to tell you. I leave it to you to practice and create some programming. So effectively, my code generation or generate code function will require the corresponding k also to be passed. The code generated till now also to be given, and then accordingly your root or your tree can be probably one parameter. Anything else I need, I can think, and effectively here at code k, I will be playing with 0 plus recursion, then code at k being 1, and then with recursion. Something like this to be planned. Whether I have to return something or not, and anything more to be done, try that, experiment, implement. Later we will discuss in more detail the next time if I am not able to implement. And of course, you will have your PQ to be accordingly implemented. You have already done extract, min, and all that. Earlier, those you have done with earlier int or struct arrays. Earlier, it was array of structs. And now, earlier you have done that, but now you will require it as array of pointers to struct. So accordingly, the return type for min, heapify, etc. will change, and all that logic you have to accordingly plan. With this, I will stop, and maybe I'll stop the discussion, leave it to you for implementation. It's a good, interesting problem. I'll suggest everyone to try, and definitely you will enjoy its programming. Bye-bye, all the best.